This video will include solutions to problems from section 6.1. And in 6.1, we talk about how to find the area between two curves. So every one of these problems is going to begin with us making a sketch, because as we discussed in class, the formula for finding the area between two curves is going to be to integrate the top function minus the bottom function. All right, so that's what we're going to do. The area is going to equal the integral of the top function minus the bottom function if we're integrating with respect to x. Or it might be the integral of the right function minus the left function if we're forced to integrate with respect to y. It's up to us to draw the graphs and determine which of those two is the appropriate choice. So I'll start with number 8. Okay. Problem 8 gives us a graph function y equals x squared minus 2x. And y equals x plus 4. And the instructions say, sketch the region enclosed by the given curves, decide whether to integrate with respect to x or y, draw a typical approximating rectangle and label its height and width, then find the area of the region. Okay, very typical set of instructions for a problem of this nature. So we're going to want to draw the graph of these two functions. Well, this is a parabola. It opens up because a is positive. We know if we factor this, right? If we factor this, we know this is x times x minus 2. So we can find the x-intercepts. The x-intercepts are 0 and 2. We could actually find, well, we know because this is 0 and this is 2, we know the axis of symmetry goes through 1, which means the vertex of this parabola, right? Because the vertex is on the actual axis of symmetry. The vertex is going to be x is 1. If I put a 1 here, I get 1. If I put a 1 here, I get -2. So the vertex of this is right here at 1, -1. Or we could have noticed that a is 1. And so we know if a is 1, our parabola goes over 1, up 1. That's our basic parabola. So we have a parabola that goes like this, right? This is our parabola. Now, right now, we don't have a region, a closed region, but we have to graph the line y equals x plus 4, right? So that line has a slope of 1 and a y-intercept of 4, right? Now, this isn't going to be to scale because technically, if this is 2, well, maybe we can fit this in. So it's going to look like this, right? The line is going to go like this. And so if we draw our parabola, we can see that the region that we want to find the area of is this piece right here. Pardon the fact that we have our right minus left going through the region. A smarter person would have moved the graph down a little further, but well, you get what you get. So how are we going to find the area of this? Well, it said to draw the sketch and determine whether we want to integrate with respect to x or y. How do we make that determination? Well, we look at our region and we ask ourselves, if my approximating rectangles are going to be vertical, then I'm going to integrate with respect to x. Okay, so if our approximating rectangles are vertical, we're going to integrate with respect to x. If our approximating rectangles are going to be horizontal, then we're going to integrate with respect to y. Now, in this problem, we could choose either of these. We have the ability to do it either way. One way, however, is much easier than the other one. If we're going to use our approximating rectangles vertically, right? If we're going to say, okay, my typical approximating rectangle. It's just, all you have to do is just draw one rectangle. So here we go. I'll just use my pin's width as my rectangle. If I'm going to use a vertical rectangle like this, no matter where I draw this green rectangle, the red function is going to be the top and the brown function is going to be the bottom. That's the behavior that we're hoping to find when we draw the sketch. We want consistency. We want one function to always be the top and one function to always be the bottom. Now, if that's not the case, then we're going to take our approximating rectangles and we're going to try to go horizontally instead. Again, the goal being we want one function to always be on the right and one function to be on the left. Now, for this problem, that does not happen. Here, if we draw an approximating rectangle at this portion of our region, we're going to go from the parabola to the line. Down here, if we draw our approximating rectangle here, we're going to go from the parabola to the parabola. Now, that's not fatal. We can solve that, but it takes a lot more effort to solve that than it does if we can keep just one function as the top and one function as the bottom, or one function is the right and one function is the left. So in this case, we're going to choose vertically because of that. Now, what does that tell me? Well, if I'm using vertically, then I'm going to integrate with respect to x, right? We have a vertical approximating rectangle. And that means that we're going to go with respect to x. Now, I like to think, instead of vertical, I just like to look at my approximating rectangle. Whichever axis it's perpendicular to, that's what I'm going to use. So here, we're perpendicular to the x-axis, so we're going to integrate with respect to x. But the real reason, of course, is because we're using a vertical approximating rectangle. So now we know where to go from here. Our area, because what we wrote over here, is going to be the integral of our top function, which is the line, x plus 4, minus our bottom function, which is the parabola, x squared minus 2x. And we said we were integrating with respect to x. All those variables are x's. Now, one thing is missing. We don't have our bounds, right? Our bounds are not there. So how are we going to find those? Well, we're going to look at our picture, and we're going to go back to our algebra 2 or algebra 1, depending on how advanced your algebra 1 class was. And we're going to figure out where these two graphs intersect. We're going to take x squared minus 2x, and we're going to set it equal to x plus 4. Now we know how to solve this. We bring this x over here. It gives me x squared minus 3x. I bring the 4 over here. That's minus 4 equals 0. That's a quadratic. It's a quadratic that factors. I don't, Mr. Stewart's being nice to us here. We didn't need the quadratic formula to factor this. So this is going to be x minus 4 and x plus 1. So we get x equals 4 or x equals -1. So this point right here is 4, and this point right here is -1. And since we're integrating with respect to x, I don't care what the y values of those intersections are. I'm integrating with respect to x. So I'm going to start at x is -1, and I'm going to go until I get to x is 4. So from here, we would simplify this integrand. So we're going to integrate from -1 to 4. We have minus x squared, we have plus 2x, right? Minus plus 2x plus x, that's going to be plus 3x. And then we have plus 4 dx. When we integrate this, we're going to get minus x cubed over 3 plus 3x squared over 2 plus 4x. And we're going to evaluate that between -1 and 4. We put our 4 in here, 4 cubed is 64, so that's minus 64 over 3. 4 squared is 16. 16 times 3 is 48. So that's going to be plus 48 over 2. And 4 times 4 is 16, so we'll put that there. Minus, now we plug in a -1. -1 cubed is -1 times our minus is 1, so we have 1/3 there. Here we're going to plug in -1, we're going to square that. That's +1, so that's going to be plus 3/2 there. Hence the reason I didn't simplify this. And over here, we're going to put -1 in, we're going to get -4. So we have -64 thirds minus another third, so that's -65 thirds. Here we have 48 over 2 minus 3 over 2, so that's going to be plus 45 over 2. And here we have 16 plus 4, that's going to be 20. Now we need a common denominator, it's going to be 6. 3 goes into 6 twice. 2 times 65 is 130. 2 goes into 6 3 times. 3 times 45. 45 and 45 is 90, plus another 45 is going to be 135. And then we have a 1 here. 1 goes into 6 6 times. 6 times 20 is going to be 120. So here we have 130 negative plus 135, that's 5, so that's 125 over 6. Now, assuming I haven't made any silly arithmetic mistakes, the area of that region is 125 over 6. Okay, I'll erase the whiteboard and come back with another example. All right, the next problem I'll work on is problem 17. 17 is y equals 1 over x. Y equals x. Y equals 1/4 x. And x is greater than 0. Greater than or equal to 0. So our first job is to draw our sketch. Now, x is greater than or equal to 0, so we don't need to worry about quadrants 2 or 3 here. We have y equals 1 over x, right? Y equals 1 over x. So 0 is not in the domain of that. As x gets bigger and bigger and bigger, 1 over x gets smaller and smaller and smaller. So that's half of a hyperbole, right? It comes down and goes like this. Then we need y equals x. We know that's a line, slope of 1, all right? That goes like this. Then we finally end with y equals 1/4 x. That's a line whose slope is 1/4, so that looks like this. And they told us that x was greater than or equal to 0, right? X is greater than or equal to 0. So we've got our region, and now we have to strategize. Are we going to integrate with respect to x, or are we going to integrate with respect to y? And remember, we said it all comes down to our desired outcome is one function is always on the top and one function is always on the bottom. Well, here, if we have our rectangle right here, remember, once we draw the graph, we can erase all this part, right? We really don't care about this. This is our region right here. Well, if we draw a rectangle here, the red graph is on the top and the blue graph is on the bottom. But unfortunately over here, the green graph is on the top and the blue graph is on the bottom. So that's not consistent. We don't have one top, one bottom. So a lot of times that would say, okay, I want to then integrate with respect to y. I want to go horizontally because it's going to be potentially much better for me. But if we do that, then over here, we're going to go right minus left. Our green graph is on the right. Our red graph is on the left. Down here, our blue graph is on the right. Our red graph is on the left. Again, we don't have a consistent one graph on the right and one graph on the left. So what do we do in this case? Well, what we do is we think about this. We go, okay, here's what I'm going to do. I'm just going to draw this line here. Now, that's not my rectangle. I'm separating my area into two different areas. I'm going to find the area of the red minus the blue, top minus bottom. And then I'm going to find the area of the green minus the blue, top minus bottom. I'm going to do two integrals. That's how I'm going to overcome this challenge. So here's one of my approximating rectangles, and here's the other one. So I'm going to use a vertical approximating rectangle. Which means I'm going to integrate with respect to x. Now you could do it with respect to y if you want, but these are already solved for x, so there's no reason, pardon me, they're already solved for y, so there's no reason to undo them and solve them the other way. So now my area is going to be the integral from 0, right? This is 0 here. We know that's 0. And it's going to be top function minus bottom function. My top function is x. My bottom function is 1/4 x dx. Plus, I'm going to integrate. Now, I don't know what number that is. I haven't found that number. I'm going to have to find that. The top function is the hyperbola, 1/x, minus the bottom function, which is 1/4 x dx. So we have some arithmetic to do here. We have some algebra 2 to do. We got to figure out where these things intersect. Now, we could do this with algebra. We could set them equal to each other, try to solve it. But a lot of times in these kind of problems, the points of intersection are not that complicated. Usually you can just plug some numbers in, and sooner, if you try some really nice numbers, it usually works. Like, for example, what happens if I try 1 here, right? If I put 1 into the red function, y equals x, so that would give me 1. What about I'm trying to figure out where the red function and the green function intersect. Well, the green function is 1/x. If I put 1 into there, I get y equals 1 again. So this point of intersection right here is x is 1, y is 1. And I found that just by plugging in numbers. All right. Over here, this point of intersection is going to be given to me when I plug in a number and 1/4 x gives me the same result as 1/x, right? I mean, we could do that with algebra. We could say, okay, 1/4 x equals 1/x, multiply both sides by x squared over 4 equals 1, move the x squared, multiply both sides by 4, and we get x equals 2. Or we could have just plugged it in. 2 divided by 4, a half. Plug 2 into here, you get a half. So this is the point 2, 1/2. Now, because we're integrating with respect to x, we don't care about the y values. So we know the first integral goes from 0 to 1, and then the second integral goes from 1 to 2. And now, what's left? Well, we integrate, all right? X minus 1/4 x is 3/4 x, isn't it? So this is going to be 3/4. Then I integrate x. That gives me x squared over 2, evaluated between 0 and 1, plus. Here I have 1/x, right? 1/x. That's x to the minus 1. Well, we know the integral of x to the -1. It's not add 1 divide, because if you add 1 you get x to the 0 divided by 0. That's the natural log of x. Minus, this is x, 1/4 is a constant, so we get x squared over 2 there, and we're going to evaluate that between 1 and 2. So now we just have a whole bunch of arithmetic to do, right? We have 3/8 x squared plus, oh, sorry, evaluated between 0 and 1, plus the natural log. We don't need the absolute value because our values are 1 and 2. Those are both positive, so we can just call that the natural value. The natural log of x minus, and here we get x squared over 8. Evaluated between 1 and 2. I'm not going to do the arithmetic. You can plug those numbers in, collect like terms, simplify, and find the answer. Okay. I'll pause the video and do one more problem for you. All right, the last problem I'll work on is number 40. Because instead of giving you the equations, in problem 40, it's problem 40 because they make you think before you speak, right? They want you to think, oh, okay, I have to find the equations, because they word it this way. It says find the area of the region bounded by the parabola y equals x squared. Okay. And the line tangent to this parabola at 1, 1 and the y-axis. Sorry, the x-axis, isn't it? Yes, the x-axis. And the tangent line. At 1, 1. So this time when we draw our graph, right, we got to do a little more thinking here. Not a lot, but a little bit. We have our parabola y equals x squared, right? It looks like this. That's our basic parabola. We have the x-axis, and we want the tangent line to the parabola at 1, 1. To find the tangent line, we first have to find the tangent. That's 2x. At the point 1, 1, the slope of our tangent line is 2x, right? So what's the equation of the tangent line? Well, x at the point 1, 1, x is 1. So at x equals 1, that means our slope equals 2, all right? So we have a line that goes through this point and has a slope of 2. So it looks like this, right? This is our line. The slope is 2. We can find the equation of the line because we can find the equation of the tangent line. We have a point and we have a slope, so we can use the point slope formula. Y minus the y coordinate, which is 1, equals the slope 2 times x minus the x coordinate, which is also 1. That gives me 2x minus 2. Bring the 1 over here and we get y equals 2x. Bring the 1 over here and we get minus 1, right? Minus 1. So that's the equation of our line. And it goes through 1, 1, because when I put x is 1 in here, I get 2 times 1, 2, minus 1, 1. And its slope is 2. So our top function is going to be the red function, right? Which is our parabola. Our bottom function is going to be the x-axis. For this part right here. But then over here, our bottom function is going to be the line y equals 2x minus 1. So again, we're going to need 2 integrals here. Right? We're going to need 2 integrals to find our area. So our area is going to be the integral from 0, right? We started at 0. Our top function is the parabola, x squared, minus the bottom function, which is x is 0. Now, we don't know where to stop because we don't know the coordinates at that point yet. We're going to have to find that. That's not a 2, that's a bad question mark. Plus the integral, we don't know that point. We do know this point, right? This is x is 1, y is 1. That's our point of intersection. So we're going to stop at 1. Our top function is again the parabola minus our bottom function, which is 2x minus 1. Dx, dx. So we need our point of intersection, right? We need to know what's the x-intercept of this line. Well, to find an x-intercept, remember, we set y equal to 0. So we have 0 equals 2x minus 1. We bring the 1 over here, 1 equals 2x, and we get x equals 1/2. So those are our bounds. Now we just integrate, right? I mean, there's nothing left to do now, but just do the work. We integrate x squared, that's x cubed over 3. We're going to evaluate that between 0 and 1/2. Here we integrate, we're going to get x cubed over 3 minus 2x squared over 2 when we integrate that. Minus a minus is plus x, and that we're going to integrate between 1/2 and 1. All right, so now we just have arithmetic to do. We put a half in here and we cube it. That's 1/8, right? 1/8, a half times a half is a fourth times a half is an eighth. Divided by 3, that's going to be 1/24th, all right? Because 1/8 divided by 3 over 1 is 1/8. You invert, right? So that's 1/24th plus, you're going to put a 1 in here. That's going to be a third. These 2's cancel. You're going to put a 1 in here. That's going to be minus 1, right? 1 squared with a negative sign. You're going to put a 1 in there. That's plus 1. Minus, now you're going to put a half in here. A half squared, half cubed is an 8. Divided by 3 is a 24th. You're going to put a half in here. When you square a half, you're going to get a 4. So that's going to be minus a 4th. And you're going to put a half in here. That's going to be plus a half. Well, this minus 1/24th and this plus 1/24th cancel. This minus 1 and this plus 1 cancel. Here you have 1/3. Here you have plus a 4th minus a half. Well, your common denominator is going to be 12. 3 goes into 12 4 times. 4 goes into 12 3 times. 2 goes into 12 6 times. And so you get 7 minus 6, you get 1/12. All right. That completes the video for section 6.1, the area between two curves.